Oh, to the left? Sure. No, I already hit record. Great. The first minute's going to be...
Oh, sorry.
That's right. Okay. So this is Encryption Decryption Part 4. The end of Lecture 3 mentions something called the Merkle-Hellman knapsack. Okay? This is Ralph Merkle and Martin Hellman. Okay? Let's talk about this real quickly. If you have a backpack and you have a bunch of items to put in it, okay, can you figure out how many items fit in there? Well, you really can. I mean, you can sit there and try every combination until... It's kind of like one of those puzzles where there's only one way they'll fit. What the Merkle-Hellman knapsack is given a set of numbers, what combination of those numbers equals a certain number. Okay? All right. We're going to see how it works. Actually, you know what? I'm going to open up this real quick here. I'm going to go back 1 week. I'm not going to go over the whole recording. I'm just going to open this one right here. Okay, and at the end, okay, I just want to cover this slide here. Okay, and this is the one. I'm going to zoom in on this one picture so you get an idea. Okay. Hopefully you can see that. Okay, I'm trying to make it visible on the screen. Okay. It says given a set of numbers S and a target T, okay, find the value between 0 and 1 such that that formula works. Okay. What I mean by that is, given a set of numbers 9, 5, 2, and 13, and the target 24, what combination of the numbers 9, 5, 2, and 13 equal 24? Well, it's 9, 2, and 13. Okay? So what we need to figure out is what values of V make that work. In other words, 9 times 1, see? 9 times 1 plus 5 times 0 plus 2 times 1 plus 13 times 1. Everybody see that? You know, multiplying times 0 is 0. Multiplying times 1 is the number. Okay. So what combination of these numbers, when multiplied by the V's, equal 24? So it's 9 times 1 plus 5 times 0 plus 2 times 1 plus 13 times 1 equals 24. Okay? And earlier in the lecture, it talks about NP complete, talks about EXP, talks about all those. Super important you go over that. All three of those are on the test. NP, NP complete, and EXP is on there as well. P is on there as well too. Yeah, P is, yes. Okay. They're all on there. Okay? And this is considered NP complete as long as you can guess it. NP complete means if I guess the right answer, I can see that it works. So if I guess 1011 for V, can I verify that it equals 24? Sure I can. Okay? Please go back and listen to the lecture. There's probably 10 questions on it. Okay? All right, and if you have questions on it, ask me before class next time. Okay, so let's see how this thing works. First thing you do is pick a simple super increasing knapsack. Okay. What we mean by super increasing is you get a number. The next number has to be greater than the combination of all the prior numbers. Okay? So the second number is bigger than the first number. The third number is bigger than the second plus the first. The fourth is bigger than the third plus the second plus the first. Okay? So why do we do that? Well, it prevents repeats. I mean, it prevents, like another thing we just did where the answer was 24 and the V was 1011. Wouldn't it suck if the answer could also be 1011 or then 1101? In other words, there was two answers. In other words, two keys to it. That wouldn't be good. With encryption, you don't want two keys that open the same thing. So we have to have a simple super increasing knapsack, and that's on the test as well. Actually, all these steps are on there. But there's a question specifically just about that. Then you got to calculate the hard knapsack, which we'll see how to do. Encrypt a message. That's all you got to do. If you can do this, you got it. Now let's talk about the math and everything behind it. Okay. It says to encrypt a message, it says receiver picks a simple super encrypting knapsack. So whoever's receiving it picks this knapsack, okay? Bunch of numbers. Okay? Okay? It picks S. Also picks a multiplier and a modulus. This is probably the most complicated math. Well, the Gloyes field in AES might be a little bit, not too bad, but So the math isn't really that difficult. Okay, so we'll say that Carol here is the receiver. She picked a simple super-increasing knapsack of 1, 2, and 6. Is that simple super-increasing? 2 is bigger than 1. 6 is bigger than 2 plus 1. So it does meet the criteria. She also picks a multiplier and a modulus. N should be prime. I'm not 100% positive if all the homework assignments and examples have N being prime, but in the real world, these numbers are too small anyway.
So the modulus is always prime then?
It should be.
Oh, should be.
Should be. I mean, in the real world, to use this, it always is.
Okay.
What I'm saying is, for these assignments I'm giving you, I mean, these numbers are normally 2 to the 200th digits long. So we are talking this humongo number. Okay? When we get to RSA, I mean, they're literally 200 digits long. So there's no way, I mean, but I could just imagine me giving you something that's that long. We try to make it easier. All right? So we selected those. Then the receiver, again, Carol over here, computes the hard knapsack. So we took the simple knapsack, these values computed the hard knapsack. Okay? How do we do this? You need to know this fourth bullet. Okay? First of all, does everybody understand what h equals h to the 1, h to the 2, h to the 3 means? Well, it means the hard knapsack is made of h's, but the first one, the second one, the third. In other words, 3 separate values. If I said h1, h1, h2, that would mean whatever is in h1 will be in there twice. Okay. But when you say h to the I, so you'd place it with a 1. So the first h is equal to the w times the first s mod n. The second h is equal to w times the second s mod n. The third h is equal to w times the third s, the third. So in other words, whatever number you replace it with, you have to stay consistent during that time. Okay. So when we use the 1, we'll be calculating h1. When we use the 2, we'll be calculating h2. When we use the 6, what will we be calculating?
H3.
h3. Exactly.
H2.
h2. All right. All right. So you do need to know this formula. Okay. Now, have I told you all about your test yet? They're take home, due online, open book.
Well, that means it's going to suck.
He's going to do
But
something about that.
in the past, I make students have to do all this math with no calculator. And I'm even talking things like 14 to the 27th power with no calculator. Kind of hard to require that at home. Actually, it's very simple to do. We cover how to do it. Very simple to do. You can do it with no calculator at home. But I can't require that at home. Because the odds of Ken back there, when I say no calculator, of him not using a calculator slim. Okay? So what do? I shorten the time limit, add more questions, and randomize the questions. So I know what your test is. We will give you a little more information about it when we get close. All right. So the first h, in other words, h1 is equal to w times s1 mod n. So then we replace them. Okay? N equals 11. Okay. No, mod n, I'm sorry. Then 11. So where does 11 come from? W. So the 11 went there. 11 times 1 mod 13. Let's talk about modulus for a second. Okay, what the heck is modulus? I can't, well, maybe I can. Hold on. We're going to draw this. If I can find a pen. If I did 11, my artistic skills are amazing. Divided by 13. Okay, you all remember that from math? Way back in wherever? You always take the number before the mod and underneath the little divisor. The little what's there? So you take the 13 at the end and put it in the front. So we're asking, how many times does 13 go into 11? 0. Okay? So what's the remainder? 11. It's not 13. So many people swap them and you end up with a 2. Because if you swap these, 11 goes into 13 once and you have a remainder of 2. That's the wrong answer, but that answer's on the test. So I did that for you guys. So if you do it wrong backwards, I thought of that for you. Okay, so we take the 11, we put the 13 in the front. How many times does 13 go into 11? 0. What's the remainder? We're not calculating decimals. We're not going to put a point, whatever. Just basic, what's this? First grade math? Second grade math? Not much beyond that, is it? Okay. So, the answer is 11. Everybody okay on the first one? So it was 11 times 1, which is 11, mod 13. So 11 mod 13 is 11. Now let's do the second one. 11 times 2 is what? 22. You guys are good. Maybe it was written right there. Okay. So 11 times 2 mod 13. So we take the 13, put it in front of the 22. So my little drawing back here, okay, I have the 22 under the divisor thingy, Uzi. Then we have the 13 out in front. How many times 13 go into 22? Once. What's the remainder? 9. Man, you guys are good. How'd you guess that? Okay, so everybody understand modulus. Modulus is the remainder. It's not rounding, it's not truncating, it's not a decimal, it's the remainder. Modulus is the remainder.
So the entirety of the remainder, even if it's 9, 5, 6, 4, 3, 3, 7?
Right, because remember, okay, let me draw out this other one. Hold on, that's actually a good question. So if I took 22, put a 13 here, okay? 13 goes into the 2, 0. Y'all with me? Goes into the 22 once. So we subtract 13. Well, okay, it's close. And we get...
Was that first grade, second grade?
Okay, that's really a 3 over there. That's a 1.
I see it now.
See it now? All
I
right.
see it now.
So we subtract the 2 and we get a 9. The remainder, remember we used to do this in school, you would write the remainder is 9. We didn't do anything about calculating decimal places. We really stopped at that point. So the answer is 9. Okay? Clear as mud? Okay, third one. 11 times 6 is 66 mod 13. Again, the 66 goes underneath, the 13 goes on the outside. The answer is obviously 1, because it's 13 times what? Times 5? 13 times 5 would be 65. Yep. So it's 5 times. So the 13 goes into 66 5 times. So you subtract 65. 66 minus 65 is 1. Remainder is 1. Done. Everybody okay? So now our hard knapsack is what? 11, 9, and 1. Everybody see that? Because remember, we calculated H1, H2, and H3. So our hard knapsack is 11, 9, and 1. Yes, maybe? Hopefully? Okay, let's continue. All right, now we're going to send a message, okay? So the receiver sends the 1191. So Carol sends 1191 to me. Okay, the receiver, Carol keeps the simple knapsack. She also keeps N and W secret. So what does she send to me? Just the hard knapsack, okay? So far so good? Now, I want to send a value to her. This only works in binary. Okay? So I'm going to send the value 101, 010, 011. The reason it broke up into 3s is because my hard knapsack is only 3. Okay? So I take the 101 and I put the 1191. So I have 11 times 1 plus 9 times 0 plus 1 times 1. It's 12. Everybody see that? Then 11 times 0 plus 9 times 1 plus 1 times 0. 9. Then 11 times 0 plus 9 times 1 plus 1 times 1. It's 10. So our ciphertext, 12, 9, and 0. So what me as the sender sends Carol is 12, 9, and 10. Did I ever know what the simple knapsack was? Nope, didn't have a clue. Did I ever know what the W, the multiplier, or the modulus was? No, I never had a clue. So really, it's good because she needs those values to decrypt them. But without them, you can't decrypt it because they all work together. So me as a sender, I just send her this value. Okay? All right. So far, so good? Maybe? All right. And here's again modulus. Okay. 33 mod 8, what's the remainder? It's actually 4.125. So what you do is you go 4 times 8 is 32. 33 minus 32 is 1. So I showed you the way how to do it. So
So you run down.
yeah, I mean, if you just want to do it this way, remember we're putting the thing in front of the 33. It actually is up to 4.125. So in other words, just a little bit more than 4. So then we take the 8, multiply it times the 4. So that's the whole number. That's not the remainder. That's the whole number. And we ended up with 4.125. So 8 times 4 is 8 times the whole number. We get 32. Then 33 minus 32 gives us a remainder of 1. And 1 is 0.125 of 8. So it's easy enough. All right. Now we need to calculate the multiplicative inverse. I'm going to show you 3 different ways to do this. And for the homework assignment, you need to do it all 3 ways. And it's important you do it all 3 ways. They don't always work, but I think they do on the homework maybe this year. I think. It's very hard to get 3 numbers to work all the time. Okay. So this is method 1. Wow, my color font matches the line. Look at that, pretty handy on the board. Okay, to calculate the multiplicative inverse of a number, take that number and w raised to the n minus 2 mod n. This is way 1. So I take n and w. W is 11, n is 13. Still the same numbers we had before. Okay. So the multiplicative inverse, this is not w raised to the negative 1. Do not bring up your calculator. You know, put in 13 exponent negative 1. This is not the same thing. This is called the multiplicative inverse. Okay? So, the inverse, multiplicative inverse of w is w raised to n minus 2 mod n. Okay? So 11, which is w, 11 raised to the n, which is 13 minus 2, mod 13. So 11 to the 11th, mod 13. Okay? What's 11 to the 11th? That big old number, mod 13. That equals 6. Easy enough? That's one way of doing it. So far, so good? Everybody here?
So you actually took that number,
I put the 13 in front of this big old number
okay.
and divided 13 into this big old number and ended up with a remainder of 6. And the modulus is, you know, the remainder of 6. So the multiplicative inverse is 6. Okay, that's method 1.
So the modulus clearly should never be larger than there, for instance. Right?
Oh, you're saying, yeah, it shouldn't be. No, it should.
So
Well, actually, hold on. Let me go back 2 slides. My modulus is bigger than the first one.
same size.
No, 11 mod 13.
Oh.
13 is bigger than 11, so what's the answer? 11. Because,
Well, 13 won't go. But
right, 13 is too big. So what's the result?
11.
11. So if our modulus, you know, mod something was bigger, then we'd end up with this huge, big old number. Which, it'd be crazy. Well, in real life, these numbers aren't that huge. But it's okay. All right, so far, okay on method 1. Let's go to method 2. Okay. All right, consider the crypto system. Here's method 2. Okay, we have our simple knapsack, we have our n and w. Okay. The comparison method. Out of all 3 methods that I'm going to show you, the one that's correct majority of the time is this one. And it's imperative you know this one because you need it later on in DES. You do something similar in DES. Okay? So you need to know how to do this. Okay. You make a chart. You put down N, W, and C. Exactly what you do. You put them on a line. N, W, and C. Okay? Just those 3 letters. Then N is equal to 13, W is equal to 1, and then comparison is nothing. Then below that, you write down 1, 0, 0. You can do that every time. NWC, 1, 0, 0. That's where you start. Then you just add them up. N, which is 13, plus 1 is 14. Plus 13 is 27. Plus 13 is 40. Plus 13 is 53, so on and so forth. So you just keep adding them up. Add up the second column. 11 plus 0 is 11. Plus 11 is 22. Plus 11 is 33, and so on and so forth. And you keep going until they match. And you always go by the W column. So you could have gone down 52 tries.
What do you mean you go by the W column? Once they match?
Okay,
they match?
once they match, whatever number of comparisons you did,
Oh, okay.
see, like, it was actually the fifth one up
Yeah,
here.
I got you.
It was the fifth on the end. We go by the W because it was where it matched. Okay? You need to know this for DES as well. So remember, NWC, write that down, then 100. Then just add them up. Don't make simple math mistakes, because then you end up with a W of 52 or something. The odds are it's going to match something sooner or later, but it's going to be this huge number if you miss it. And some of them you're going to be doing for your test end up with like 27s and 29s and 33s. So it might be a fairly large number. Okay? Are we okay in method 2? It's actually very simple.
Yeah, that's easy.
I mean, if you compare it with method 1, I mean, you actually have to do some little bit of math. Here you just add numbers.
That's, you know, you need to get a pencil, paper.
Yeah,
calculator,
it's
now.
super easy. Okay, just remember, 100. It's not 010, it's not 011, it's not 111, it's 100. Then you just add them up. Okay? Okay for method 2. Remember, method 1 was W to the n minus 2 mod n. Method 3 now is W to the W mod n. Okay? W to the W mod n. That's the third method. Okay. You like them little colors there where they all come from? So in this case it ends up being the same because W to the n minus 1 ends up being the same thing. But yeah, so W to the W mod n. So it's 11 to the 11th mod 13. And 11 to the 11 is a big number, mod 13, and you end up with 6 again. Know all three methods. And while we're at this point, I'm going to show you something. Your homework assignment is to be completed in the quizzes area. Now, I was nice enough to print out exactly what you're going to see. There's no time limit on the quiz, by the way. Start the quiz, and I think it's set to 2 hours, but it won't ever quit. Save your work as you're going along. Go back into it if you want. It'll never close on you. Just make sure you save your work. This is how I give it to you. I give you some numbers. I want you to calculate the comparison, n to the W to n minus 2 and the W to the W. And you do that a few times.
Shouldn't they be the same, or did you change the numbers around?
Oh, I changed the numbers around.
In
See?
each question?
11 and 9, 2 and 11, 22 and 9.
Well, right, but won't the mod be
They should be.
the same within the question?
Hopefully.
Oh.
They're not
Yeah,
always.
right.
But you just gotta know how to do it with each of the.
With
You
each
need
of
to
them.
know how to do it with each of
Yeah.
them. Because later on, I might tell you use this method. And it might be a different value. And if the comparison came up with a different value, and then you use the other one, and then just know how to do all three. And the reason I'm having you do it in the quizzes area was, I always had people do it on paper, and nothing against you guys, but your writing sucks. Okay? Half the time I'm like, what the hell? Okay, mine sucks too. Okay, everybody's writing sucks. I couldn't read it, or you wrote it in a format that I couldn't follow, or it was like someone would go through all the method ones, and then they do all the methods. So I'm trying to grade them. Like, okay, there's this one, method 1, and 12 pages later, it's this one, method 1. It's like, no, it was. So I said, you know what? I could put it in the quizzes area. Okay, easy enough. So I just want the answers. In other words, I want the answer of 6. You don't have to put a big old long stuff in there. If you put anything other than just the answer, it's going to mark it wrong. Then I'm going to look at it and say, why did Carol get a 0? Then I'm going to have to go through there and manually grade each one. So all I'm looking for is the answer. So if the answer is 5, 5. Don't put W to W mod n equals 5. I know someone's going to. It happens every time. Someone's going to do that. They're going to say W raised to W, and I'm going to get the email. I can't figure out how to make a W to the W in the Dropbox or in the quiz. I'm like, just put the answer. Okay. Just put the answer. Is everybody okay on the three methods? So far, so good?
Kind
All right. Now let's how to decrypt a message. Here's where it gets a little tough. It's just this way. I'm going to show you where you're going to mess up. And luckily for you guys, the way you're going to mess up is on the test as well. I put that there for you. It makes it easier. Okay. So, we know this from the previous slide, believe it or not. We do. There's some associated property of math. We basically know the first 2 lines. Okay? Because remember the hard knapsack was W to the, remember it was H to the 1 was equal to W times S to the 1 mod N, remember that? Okay, and then, so it's all the same stuff, okay? Now, let's go down and go to this line right here, line 4, okay? So the inverse, multiplicative inverse of W times C to the I, what's C to the I? The first ciphertext, in this case would be 12. So the inverse of W times C to the I is equal to S times P to the I mod N. Okay? Now let's walk through it so you can see what I'm talking about. Okay? Remember, the inverse of, multiplicative inverse of W is 6. Our ciphertext is 12, 9, and 10. So we take our multiplicative inverse of 6 times 12, because that was our first ciphertext. That's equal to 72. 6 times 12 is 72. Mod N. Okay? And we did, yeah, mod, okay, and yeah, N is 13, yeah. I didn't write that, did I? Okay. The mod should have been 13, let's make sure. Yeah, it was, right there. N is 13. Okay. So it's inverse of W, multiplicative inverse of W times the ciphertext value, mod 13. So 72 mod 13, so if we take 72, put the little bracket thing over it, put the 13 in the front, we end up with a 7. Okay? So is that 7 in the binary? I think it is. No, it's not. No, it's not. So how did I possibly get that? Let's verify that's not 7 in binary. Just to prove that it's not 7. We're going to go 7, convert to binary, and it's 111. Well, crap. So is there an error in my slide? No, there's not an error in my slide.
101 is 5.
Okay. Show you what you do. So you end up with 7. Okay. What combination of the simple knapsack equals 7? 1, 0, 1. So the 1 and the 6. So when we do the second value, 6 times 9 is 54, mod 13, get 2. So what combination of the simple knapsack give you 2? 0, 1, 0. Everybody see that?
Yes, now.
Okay. So you follow me here. 6 times 9 is 54. Mod 13 is 2. Okay. So now we take that 2. What combination of our simple knapsack, which was 1, 2, and 6, which combination of those numbers equals 2?
0, 1, 0.
0, 1, 0. Exactly what I got.
You gotta superimpose whatever he's got down there over the 1,
Right.
2, and the 6.
Yeah, basically.
It's not binary. See, y'all thought I messed up. See, I didn't. Okay, so 6 times 10. This one's tough. I'll do it for you. It's 60. Okay, mod 13, you get 8. So what combination of those numbers will give you 8? 0, 1, 1. Everybody see that? Easy enough? Now, what you're going to do, I'm telling you right now, you're going to turn in 7, 2, and 8. So many people do that. And luckily enough, they will be on the test. So if you want to turn those in, I'm ready for you.
Does anyone ever get like
but-
a passing?
But for some reason, the grade on 7, 2, and 8 is going to be 0. So, okay. That's called the intermediate value.
When you go to decrypt, you already will have the knapsack?
Remember, I sent this to Carol. Carol kept the simple knapsack, and she also kept N and W. Remember, all I had was the hard knapsack.
Okay.
So I sent her something encrypted with her. So she already had the simple knapsack. So now all she needs to do is put that puzzle back together. What combination of these pieces equals 7?
Oh, this is her.
Right, this is her decrypting the message.
Okay, now I thought.
Yeah, this is Carol using the simple knapsack along with N and W to decrypt what I sent her. Because I sent her that,
But hold on, so that...
wherever it was, that one. Go ahead.
So you're saying that the simple knapstack is gonna stay, once it's created, it's static?
Correct.
That's not true, though.
What do you mean?
Because once you create a key, a public key, it doesn't always stay that public key.
Well, for that time we're encrypting, it is. Remember, she's going to send me something. I'm going to reply back with something I just encrypted. Now, she can send me something later with a different key. That's totally fine.
Oh, okay.
But for this
So then-
specific thing,
Okay, for that transaction instance,
right,
it's gonna say, okay.
yes,
All right.
okay, all right. So far so good? All right, so let's walk through an example. Here's exactly what you're going to see it on the test. So we have a simple knapsack of 1, 3, 6, 11, and 13. Okay? So h to the I is equal to s to the I, well, that's supposed to be a small I, times w mod n. It's called the general formula. Okay? The general form you'll see it referred to as. So, h to the 1 is 1 times 11. Remember, 1 came from the simple knapsack. 11 is the w, the multiplier, mod 13. Okay? 11 mod 13 is 11. Just so happens the same number. 3 times 11 mod 13. Remember, the 3 came from the center value. H to the second came from the s to the second. So 3 times 11 mod 13. So we get 33 mod 13. Ends up to be 7. Then 6 times 11, the 66 mod 13, we end up with 1. So, what is Carol going to send me? Remember, Carol's doing all this work so far. What? Right, she sends me 1171 and nothing else. That's it. She said, Ken, use this key. Okay? I don't know, I have a clue what she used to create it. I just know that that's the key. So Carol sends me 1171. I take that, I encrypt something, send her the ciphertext, and she's the only one in the world that can decrypt it. All right. So, now assume again that the simple knapsack is 1, 3, and 6, and the multiplier is 11, and the modulus is 13. Encrypt this value. So now this is me. Okay? Now I have the hard knapsack. Now, I gave you all this information up here. I gave you the simple. Did you really need it? No, I didn't need it. Because encrypting something, I don't need the simple. I just need the hard. I probably need to change that question to show the hard. Yeah, I bet if I probably need to reword that and only show the hard knapsack up there. But either way, there's the hard knapsack. So we put the 101 below the 1171. We put the 010 below the 1171 and the 011 below the 1171. Then we get 11 and 0 and 1. We end up with a 12.
Where did you get the value 101, 10, and 11?
Oh, that's what I came up with.
Okay.
That's the message I'm going to send you. So that's my plain text. Remember, it's in binary. My plain text message is 101, 010, 011. Now, if I had a 4-digit hard knapsack, I can get 4 binary digits at a time. If I had a 200-digit hard knapsack, I could do 200 digits at a time. We're just working with small numbers here. I think you guys have to do with 4. Okay? And we end up with 12, 7, and 8. So I send Carol 12, 7, and 8.
And her having that key
She can decrypt it. Okay? Why isn't it changing? Whoa, what the heck?
What'd you do?
I don't know.
Goodbye.
All right, we're back. Yes. Okay, let's make sure I didn't skip a page here. Okay, we did that one.
Yes.
Okay, now we're going to decrypt something. Now you'll notice here I'm decrypting something different. Okay, remember I encrypted and got 12, 7, and 8. Remember that? I'm decrypting something different. There's a reason for that. So Carol now has her simple knapsack, her multiplier, and her modulus still. She's the only one with that information. All of it. 11 and 18. We calculate the multiplicative inverse of W, which is 6. Remember, it's based on these two, and then we use the same example. So, all right. So we have W inverse of W times C to the I mod n gives us an intermediate value. Okay. So 6 times 19. See where the 6 came from, the 19 came from. 6 times 19 mod 13, you get 10. Okay? 6 times 18 mod 13, you get 4. That's just the result. I mean, we could put it in a calculator, but that's what the result is. All right? So now that we have a 10 and a 4, half of you are going to submit that on your test. Trust it's going to happen. It's going to happen. It happens every time.
And it's one of the answers too, right?
Oh, yes, it will be there. Oh, yeah, I had to make sure. I hate to do all that work and not have the right answer.
couple of them aren't gonna have the right answer, it's just gonna say nothing at the bottom. The answers are correct. So.
I've actually before, you know, in the Dropbox where I can put instructions in there, I actually put instructions in there once in white font. And it was something like, email Ken here to get extra credit. And like one person found it. And the only reason they found it, they happened to be dragging their mouse and clicked the button and went, whoa, the page lit up. Yeah, one person found it. And I've also taken the PowerPoints before and I changed the binary on one of them. I think it's still on one of these. I don't know which one though.
Oh, great.
So, all right, let's continue. So we got 10 and 4. That's our intermediate value. So what combination of 1, 3, and 6 equals 10? 1, 1, 1. Easy enough. Is there any other combination of 1, 3, and 6 that can equal 10? Well, no, it's all of them. Okay. Okay. So what combination of 1, 3, 6 equals 4? Well, 1 and 3. Is there any other way we could have done that math? No. Well, the whole point of a super increasing is to prevent the ability from doing it in multiple ways. You don't want to be able to do it multiple ways. Because, I mean, can you imagine if we could do 4 differently? So the answer is 110 or 101. I mean, no, that's not going to cut it. Okay? So the answer, or the plain text, is what when you got ciphertext and you decrypt, you want plain text. The plain text is 111, 110. Easy enough? Isn't this easy? Super easy. It's like 87 steps, but it's very easy. All right. So now let's talk about the algorithm in general. N is normally 200 bits long. So that 13 we've been working with? No. In the world, I mean, that would take a computer like no time. If you guys can figure it out, I mean, obviously a computer interference. So really, it's 200 bits long. Okay. The simple knapsack values are chosen to be 2 to the 200th apart. So instead of 1, 3, and 6,
2 to the 200.
apart. So if the first one's 1, the second one is like, what, bazillion, some odd number?
2 with 200 zeros.
Yeah. And then the third one is 200 zeros past that. Then the fourth one is 200 zeros past that. So you can see they're very large numbers. Okay? So choose M. So in other words, choose the number of random digits between 0 and 2 to the 200th. Okay? So the simple knapsack is basically 2 to the 200th in length. So it can be crazy. Okay? So each term used in this simple knapsack is between 200 and 400 bits long. So that 1, 3, and 6 is not really a good representation of a valid number. Okay. So if I was to write a program in Java, what would I need to use to handle something like that? Anybody? The big integer class, just so you know. I actually did a podcast over that this weekend. I remember that. So it would take 10 to the 47th years to try every combination of 2 to the 200 digits, you know, for each of the S to the I. So it's going to take you a few days to break this encryption. Okay. And it's hard to break for large values. Duh. Okay. All right. There are some weaknesses, though. Shamir in 1980 says if the modulus is known, it is possible to determine the simple knapsack in polynomial time. Okay. I talk about polynomial time in the prior lecture, which one of you watched. Maybe 2.
I watched it.
Okay, good. 3.
3.
So we're doing good. What we mean by polynomial time is it can be a considerably hard program, like a P problem. I talk about finding a book in the library. Y'all been to the library? Y'all know where that is? No one ever uses it anymore. I think what? Free Wi-Fi? Checked out a book?
Yeah.
Seriously?
Electricity and Magnetism, 1990.
Wow. And it wasn't an ebook? Okay. But the point is, it could be, you know, you ever seen that show called Treasure Hunters? It was on for 1 season, I think. They actually had to go to the Library of Congress, and they had to search through a card catalog and find this one weird book somewhere. Was it a difficult task? No. They really just had to look at each book and see if it's the book they wanted. So it might have taken them the rest of their lives. But it wasn't difficult. So what he's saying here is, if n is known, you can calculate S. It might take you the rest of your life, but you can calculate it.
And it's like the library, you just have to find the book you're looking
Right. You could literally search the entire library until you find it. But it's not difficult. Okay? All right. Okay, here's exactly what the test questions are going to look like. Also, I mentioned somewhere that the Merkle-Hellman knapsack is a one-way encryption system. Did I mention that in the other slides?
Yeah.
Okay. That's question like 12, like on 3 tests. So just saying. Okay. So now I'm going to remove it. Because now y'all are going to remember it. I'm going to remove it. And you're like, darn it, I knew that. Okay, so here's the way I say it. Assuming this simple knapsack, compute the hard knapsack, encrypt its value, compute the inverse of W and decrypt. It's exactly how you get to see it. Okay? So it's 4 things. And I think what I do is, there's 4 separate questions on the test. It's all of the top part, including compute the hard knapsack. Then it's the top part, including encrypt this. Then it's the top part, including compute this. So you can do each one. Okay? Everybody happy? Totally understand this? No?
Yeah, I'm not even
Yeah.
practicing.
All right.